So now that we've given a quick overview of reactive programming, let's talk about the structure and the functionality of the Java Completable Futures framework, which is one of several ways of achieving bits and pieces or all of the reactive programming concepts and principles in the context of modern Java. So we're going to talk about what the Completable Future framework looks like, how it's structured, what its behaviors are, and basically the programming paradigm that it provides. The Java Completable Futures framework provides an asynchronous and reactive parallel programming model, which is quite a bit different from what we've been talking about heretofore, where we've been focusing almost exclusively on synchronous programming using Java streams and parallel streams. And you'll see that it also gives you ways of being able to achieve those different properties that are the cornerstone of reactive programming. As a baseline to make the discussion more concrete, let's consider a web crawler implementation that's synchronous. This is very much like what you did for one of your first assignments, which was the synchronous streams version of the web crawler. So if you think about what it's going to do, you start by getting the start page, the intro HTML page, or the root of all the other pages you're going to traverse. You then, in the next step, count the number of images on that page. Then you count the number of images on all pages reachable from that page. In other words, all the hyperlinks, you traverse those recursively. And then finally, the last step, step number 4, you're going to combine all the results together to create the total. Okay, pretty straightforward, very much like what you've done so far. And the way to think about this is that the time needed to perform all these steps is the sum of each of these steps done sequentially. And when you actually run your sequential streams crawler, or your sequential loops crawler for that matter, you'll notice if you watch it and you keep track of the time and you literally watch the GUI as it's running, it's pretty darn slow, right? Because it's one thing after the other. So is there a better way to do this? Well, yes, there's several different ways to do this. One way to do this, of course, is to use parallel streams. But another way to do it is to use Java's Completable Futures framework, which supports dependent actions that trigger upon the completion of asynchronous operations or async operations. So let's kind of take a look at how this might work. So what we're going to do here is we're going to have task 1, and we're going to start downloading the start page, but we're going to do it asynchronously, which means we say download the page, but we don't wait for the results. We just start the download. And we're going to get back something we'll talk about in a minute called a completable future. And then we're going to have task 2 and task 3, which can now run in parallel. And task 2 and task 3 are triggered when task 1 completes. So when we finish downloading the web page, then task 2 and task 3 can start to run, and they can start to run in parallel. So what we're basically doing there is we're forking off 2 new asynchronous tasks when the first asynchronous task completes. And task 2 will count the number of images on the page asynchronously. And task number 3 will count the number of images that are reachable from that page via the hyperlinks. And that will also be done asynchronously. So now we've got task 2 and task 3 that are running. They're basically doing their computations. And they also are going to return something called a completable future. Each one will return a separate completable future, as we'll see in a second. And then task 4 will run when both task 2 and task 3 are finished. So not until task 2 and task 3 are done will task 4 get done. And task 4 will combine the results that will create the final total asynchronous. You could also do it synchronously too. We'll see that when we look at the implementation. So what's nice about this is a couple things. First, we're modeling the flow of control by a data flow diagram. We're also showing how you can do things asynchronously. We're showing how you can split things or fork stuff off and things can run in parallel. And then we're also showing how you can join results back in order to get the final result computed synchronously or asynchronously. And something I'm not really showing here, but it's also very important, is that task 3, where we're going to count the images of all hyperlinked pages asynchronously, itself could recursively use this entire data flow model on each hyperlink. So each hyperlink that we have on a given page will then trigger this whole process to run asynchronously as well. So you'll see that as we get into this, that there's lots and lots of room for asynchronous computations. Here's basically a little bit more kind of pseudocode. They're showing what's going on. This is a little bit, this is kind of high level, just a data flow diagram. This is now getting into what the code would look like. I'm still keeping it high level to avoid getting you distracted by too much syntax. But basically what we're doing here is task 1 is going to make a call to a completable future method called supply async, giving it essentially a computation to run. So it's going to go ahead and run that computation, and it's going to get back this thing called a completable future, which we're going to call page. And you should think of this as like a table tent number. So if you ever go to a fast food restaurant, they used to do this with little pieces of plastic. Now they just give you a piece of paper with a number on it. But back in the day, you would go and order something at a restaurant like, say, Wendy's. And if you ever go to Wendy's, what's their big thing? Cook to order. So everything's cooked to order. So when you order your food, they don't do what they used to do at McDonald's, where you would order a Big Mac and fries and a drink, and the clerk would take your money, reach back to the heat lamp, get the French fries that were pre-made and cached, get the Big Mac that was pre-made and cached, get the drink that was pre-poured and cached, synchronously hand it back to you, you go on your way. And so that's a good example of synchronous communication and synchronous interaction. With Wendy's, you order your food, they're going to cook it to order. They don't want you standing there waiting, blocking the cash register, because that's their cash flow, of course. So they will instead give you a table tent number, either a physical or virtual table tent number, and then you will go off and do something else while they cook your food. And when your food is done, then they will either come out and deliver it to you, which is a callback model, or you will come back to a window and pick it up, which is a polling model. And those are the two ways you can get your table tent number future redeemed. And the same basic idea is going on here. So we get back this thing called a completable future, and that will be redeemed when the order is ready, the order here being downloading the page. So what's happening here is once we get this particular page, then you can see we're going to use this for task 2 and task 3. And you can see how these two things then, once the start page has been downloaded, then what we're going to do is we're going to go ahead and apply another call asynchronously to count the number of images in the page. And we're going to also call then compose async in task 3 to basically do some stuff that processes all the links that are reachable from that page. So these two things will run in parallel. And notice how they themselves return completable futures, which I use as different table tent numbers just to make it visual. And so image 1 and image 2 are the table tent numbers here. And then task 4 gets to run when table tent number or completable future 1 is done and table tent number completable future 2 is done. And when both those things are done, then we can combine the results together and then compute the sum of the results. And again, as I mentioned before, task 3 itself will then recursively, for every hyperlink, do the whole thing from task 1 to task 4 for each of the recursive hyperlinks. So as you can see here, these asynchronous operations are being forked, chained, and joined together in a very flexible way. The async programming model that is provided by Completable Futures resembles synchronous programming in the sense that you have one thing followed by another, even though things are actually running asynchronously. And the way it does that is by something called completion stages. And we'll talk more about completion stages here shortly. A completion stage is another variant of the fluent interface pattern that we've been talking about in the context of Java streams. It's just that this is done triggering things when asynchronous computation is complete. So it's slightly different semantics, but it's syntactically very similar to what we've seen with the fluent interface patterns we've been talking about with Java streams before. All the asynchronous operations can run in a thread pool, and that thread pool can either be the common fork join pool, which is what it is if you don't provide a specific pool you want it to run in. It could be a custom fork join pool. It could be some other kind of either predefined or user-created, customized thread pool. So there's lots of flexibility with Java Completable Futures in order to be able to run the computations in parallel in a thread pool of your choice. In contrast, Java parallel streams really limits you to the common fork join pool. There are non-portable ways of getting your own fork join pool, but it's very uncommon to use those. It's better to stick with a common fork join pool with parallel streams. But completable futures gives you more flexibility. Now, how long is it going to take to do these computations? Well, the time needed to perform these tasks really depends on how well the tasks can be parallelized. And this is something that's known as Amdahl's law. And the speed up is basically a function of the part that you can parallelize based on how many workers and how much you can parallelize. And then you still have to add that to the part of the job that cannot be parallelized. And that gives you the speed up that you can get with respect to performance. So in this particular example, you can parallelize it very well because it's basically a bunch of embarrassingly parallel computations. And therefore, we can get it to run quite nicely. And depending on various factors, it could scale relatively linearly with respect to the number of cores, although you're incurring some networking overhead, so that'll bring down the performance just a bit. The entire Java Completable Futures framework resides in a single class with over 60 methods in it. And that's kind of daunting. So we're going to talk about, when we talk about completable futures, we're going to split it up into a bunch of different sub-chunks. So we'll have things that are factory methods and basic methods and completion stage methods, exception methods, arbitrary arity methods, and so on and so forth. So you'll get a good feeling of how all these different mechanisms and groupings of methods work together. And that will help you navigate this particular API. Now, interestingly enough, you can actually combine completable futures, sequential streams, and functional programming features in Java quite nicely. So there's some stuff that we'll talk about where we'll show how you can actually make them all work together. They fit together pretty well. So you can actually use streams to give you the structure, whereas you can use completable futures to give you asynchrony. Now, as we will see, that there's perhaps better ways of getting that kind of a design. If you want if you want asynchronous streams processing, you're actually probably better off using reactive streams implementations like RxJava or Project Reactor, which we will also cover. But just be aware that if you're limited solely to what's available in Java, modern Java, without getting outside the scope of what you get out of the box, then completable futures and sequential streams can work together very nicely with other functional programming features like functional interfaces, method references, and Lambda expressions. Another nice aspect of completable futures is you don't often, or you rarely need to use any explicit synchronization. You don't need to use locks often, and you probably don't need to spawn threads directly when you program with the completable futures framework. And that will alleviate many inherent and accidental complexities of programming with parallel computing. So you're better off, as you've learned, hopefully, by looking at the implementation code for parallel streams, you're much better off not having to write threads yourself. You're shielded from those kinds of details. The way that this is typically handled under the hood is that the Java class libraries handle the locking that's needed to protect shared mutable state. And this would include things like I/O. This would include things like concurrent hash map. So you can often push a lot of that synchronization detail into existing classes so you don't have to worry about dealing with those things yourself in your code, which is a really nice improvement over what you do if you programmed with earlier versions of Java. So that's the end of our quick walkthrough of the structure and functionality of the Java Completable Futures framework. Again, I wouldn't expect anybody to take what we just discussed and start writing code, but don't worry, we will get into all that stuff in great detail here shortly.